Okay, so we're going to talk now about a replacement rule, or two replacement rules actually, which are called De Morgan's laws. And De Morgan's laws, there's two of them, uh, and they come up quite often in logical proofs. It's a very common pattern of reasoning in logic and mathematics. A lot of the time, it's called the crank rule because a lot of derivations or a lot of proofs are just a bunch of repeated iterations of De Morgan's law over and over and over again. Again, this is the kind of thing we could prove. One way that we could prove this is semantically by the use of truth tables. So, say for example, we wanted to prove this version of De Morgan's law. We could put both formulas on a truth table. I mean, we've seen this before, right? This is just a refresher. So we have not P and Q. So P and Q is false everywhere but on the first line. Remember, you can look at the characteristic truth tables to remind you of this. So it's false everywhere but on the first line. And then so this negation, that's the main connective in this sentence, is just going to flip all of these. So it becomes false, true, true, true. So now what about not P or not Q? Remember, that's true. Any disjunction is true on any line of the truth table where one of the disjuncts is true. It only takes one. So because these are both negated, we're looking for any line where either P or Q is true. This sentence will be true on that line. No, excuse me. We're looking for a line where either P or Q is false. Because if P is false, then not P is true. And if Q is false, then not Q is true. So we're looking for any line where either P is false or Q is false. That'll make this sentence true. So that's anywhere but on this first line. Here they're both true, so this sentence is false. Here Q is false, it's true. Here P is false, it's true. Here they're both false, so this sentence is true. So you can see that these are logically equivalent sentences by means of the truth table. Let's see how we could go about deriving that using a syntactical proof or an SD style derivation proof. Now, even though these are very common equivalencies, there are complicated to prove, and that's why there's this special rule in SD+, because you would spend a significant amount of your time that you spent doing proofs just proving De Morgan's law otherwise. All right, so because these are long, we'll start with this one. Because these are long, I'm just going to write the right to left or the left to right derivation, then I'm going to erase it, and then we'll do the right to left derivation. So first we're going to show that on the assumption of not P and Q, then we get not P or not Q. So this is an assumption. Okay, so we're trying to get this. It doesn't look like there's any direct way to do it. So what we can do is to assume the negation of what it is that we're trying to prove. So assume for purposes of negation elimination. Okay, so from here, maybe what we could try doing is assuming not P So if we have not P, then we obviously can use disjunction introduction to get not Q. So probably we can assume not P and show that we get a contradiction by using disjunction introduction to get this. Then we'll get P, and then maybe we can do the same thing on the assumption of not Q to get Q, and then we'll have P and Q, and so a contradiction with line 1. So again, this is an assumption for negation elimination. We get this just by disjunction introduction on line 3. So now we just have to reiterate line 2 down into this subderivation. And we can conclude that P now. By negation elimination on lines 3 through 5. And now we're going to kind of do the symmetrical thing with Q. Oh, excuse me, with not Q. Again, assume for negation elimination. So we'll do disjunction introduction and then reiteration to get a contradiction. Yeah, I'm sorry, this should have been 2 reiteration here. So again, that's why you should always do these in pencil, right? There's always these little mistakes that creep in. And now we have Q on line 10 by negation elimination, lines 7 through 9. So now we have to kind of adjust here. We weren't writing small enough. But we can put P and Q together with conjunction introduction. It's lines 6 and 10. Now we can reiterate line 1 down there for line to make it to have a contradiction. And we can close this out. We've shown that on this assumption we get a contradiction. And so we can take this negation off, assuming the negation of this got us a contradiction. So not P, or not Q, negation elimination, 2 to 12. Okay, so let's go back the other way now. Let's go from not P or Q to not P and Q. Not P or not Q. we're trying to get to not P and Q. Alright, so it looks like the natural way to do this is probably by just junction elimination. Okay. So we'll assume not P and show that not P and Q follows, and then we'll do the same with not Q. So what can we do here? Well, probably the way that we can get this is by using negation introduction. So we'll assume the opposite of it and show that we get a contradiction with not P, which should be fairly obvious. So we have not P on line 2, so we can go ahead and we want to go ahead and reiterate it into here. Now what we can do is conjunction elimination on line 3 to get P. So we have P and not P. And so our line 6, we'll use disjunction introduction, lines 3 to 5. Yeah, negation introduction, lines 3 to 5. Negation introduction, 3 to 5. Alright, so now we need to do the same thing with not Q, and this is pretty much just going to be symmetrical. It's going to be a repetition of what we just did. So that's an assumption for purposes of disjunction elimination. We're going to assume P and Q for purposes of negation introduction. We'll reiterate not Q into there. And then we'll use conjunction elimination on line 8. To get our contradiction. So we can go ahead and close this little subderivation out. And we have our line 11 by negation introduction 8 to 10. And now we can conclude what we wanted by disjunction elimination. Lines 1, 2 through 6, and 7 through 11. All right, so that concludes this direction. So we have this first version of De Morgan's law. We have that done. Let's go ahead and take a look at this other one of De Morgan's laws, this other replacement rule. So let's go ahead and do left to right first. Okay, so I think the easiest way to do this direction is going to be to show that we can't have P and then show that we can't have Q. And the reason that we can't have P is if we assume P, we can use disjunction introduction to get this and we'll have a contradiction. So let's go ahead and show that. So what we're trying to prove here is not P. So let's assume P and show that a contradiction follows. So we're assuming P for purposes of negation introduction. And this is fairly simple now. We use disjunction introduction on line 2. Okay, and now we reiterate this down. It's a reiteration on line 1. We have a contradiction, so we can close this out, and we have not P on line 5 by 2 through 4 negation introduction. So now we're just going to do the exact same thing but assuming Q to get not Q. So we assume Q for negation introduction. We're trying to get not Q. And we just do the same thing we did up here. We're going to do P or Q by disjunction introduction. Now we're going to get not P or Q. Or we're going to reiterate not P or Q from line 1. And we can close this out and conclude not P, not Q. Six through 8, negation introduction. And we're done. We can go ahead and use conjunction introduction to get line 10. So lines 5 and 9, conjunction introduction. And that concludes this direction of the proof. So we can go ahead and do the right to left one now. And I have a feeling this one is going to be a little more of a pain. Let's take a look at it and see. So we're assuming not P and not Q, and we want to show that we get not P or Q. All right, so how can we do this? Well, one way that we might be able to do this is we should probably assume the opposite of what it is that we're trying to prove. I think that's the way to go about doing this. And then we'll use disjunction elimination. So we're making this assumption for purposes of negation introduction. And it's fairly intuitively obvious here that we have a contradiction, right? We have either P or Q, but we've already established that not P and not Q. So let's assume P first. And what we're trying to get here is a contradiction so that we can conclude so if we reiterate this down, we'll have a contradiction. We could get not P, but not P is not going to help us at all. So let's see, I'm actually a little bit stuck here on this one, trying to think about how to go forward, because we have a contradiction, right? But the question is what we want to bring out of here, what it is that we want to get out of this subderivation in order to establish a contradiction. So one way we could do this is to show that we get P. Yeah, here's an idea. Why don't we show that on either one of these assumptions we can get P. So we can get P if we have P, and we can get P if we have Q, and either way it'll be a contradiction with line 1 here, where we have not P and not Q. So maybe that was didn't make that much sense when I explained it, but let's go ahead and run through it. Okay, so we assume P. For purposes of disjunction elimination. And if we have P, we can conclude that P by reiteration from line 3. All right, now on line 5, let's go ahead and assume Q, the other half of this disjunction, okay? Now what we're trying to do is establish that we can get P from here, and we can get P because we have a contradiction, right? Remember, when we already have a contradiction, if we're trying to establish something from that contradiction, we assume the opposite of what it is we're trying to prove. So let's assume not P for purposes of disjunction elimination. Okay, now we're going to bring not Q down from line 1. That's line 1, conjunction elimination. Okay, and now on line 8, we are going to reiterate Q into this subderivation. So now we have a contradiction. We can close out this subderivation and assume P. That's 6 through 8, negation elimination. Sorry, so that should be a negation elimination, sorry. Okay. So now line 10 here, we've shown that if P then P and if Q then P, so we can get P on line 10 by disjunction elimination, lines 2, 3 through 4, and 5 through 9. All right, and now that we have P, we can go ahead and get a contradiction here by bringing down not P from line 1 using conjunction elimination. So we've shown that the assumption of P or Q gets us a contradiction. It gets us P and not P. And we can close this out. and we can conclude not P or Q by negation introduction, lines 2 through 11. So there you go. That was actually quite a challenging derivation, but that establishes both of De Morgan's laws.